So let's get back to the lecture or the topic of non-rigid structure from motion. I'm just going to summarize a few things that have happened in recent years. Now, bear with me, this is material that goes a little beyond what I can cover in this class. So if you want to learn more about this and other very exciting topics, please take my computer vision class. You may also be interested in photogrammetry, as I keep saying, and certainly machine learning. There are many methods that are being used these days in image processing and computer vision that are borrowed from machine learning. Understanding how machine learning works is actually becoming fundamental for practitioners in in computer vision and image processing. Okay, and that is especially true for non-rigid structure from motion, as I'll talk very briefly today. So, as a reminder, we have a video sequence like this. We are given these point correspondences again. If you want to detect point correspondences, you can use the methods that we have derived here in this class, but those methods don't work as well as you would expect for complicated scenes like a moving face, because when first of all, the face is non-inversion, right? It's not an inversion surface. In fact, the face, it's human skin in general. It's super complicated to model, right? It's not that it's non-inversion. There are many objects that are non-inversion that can be easily modeled, right? Like a shiny plastic that can be modeled in actually pretty easily. But the human skin, what happens is that you have different layers in the skin, right? Under the skin. And when you have a light source here, some of the energy bounces back, right? And that we can compute with our hemisphere that we have introduced and all the incidence and radiance and all the things that we have talked about. But some of the energy actually gets absorbed by your skin, right? And that is why, not today, but in the middle of the summer, you go out and you heat up really quick, right? Because the sun, the light that comes from the sun, is actually giving you energy, right? It penetrates the skin and it gives you that sensation of being warm. And well, what is being warm? It's just that you're adding energy into the system, right? So what happens is the light goes inside your skin. And then, of course, the skin is made out of cells, right? And this light starts bouncing back and forth, right? And at some point, from this back and forth, exits the skin at a different position, right? At the distance, say, d, from the original incidence position. And modeling this is just mind-boggling, right? It's super complicated because it's not that all the light sources are going to be reprojected back into the air at the same distance d. It's that some of them are going to bounce in that other direction and will go through here. Some other ones will exit here. Some other ones will exit here, right? So there is a scattered set of light sources that vary depending on the properties of the light, the properties of your skin, whatever, right? There's many different things that influence this. So that's why in computer graphics, even to this day, you can see really, really super realistic scenes, objects, but not human faces or humans in general, right? And if you have noticed in most computer graphic generated humans, the human is really small, always wearing a lot of clothing, so there's very little skin that needs to be modeled, right? And the face is usually not prominent, right? Because it creates this creepy uncanny valley, some people call it, right? That gives you the impression that this is not really something too abstract, that I can consider not a human, but I cannot consider it a human, right? And the closer you get to a human modeling of the skin, the worse it gets, actually, if it's not perfect. And that they call it the uncanny valley, right? Because it goes from bad to worse before it gets really better, right? Super complicated to model these things. Now, they do get modeled, but the resources that you need, the economical resources and the computational resources you need to do that, it's just extraordinary. Obviously, companies like Pixar and Disney, who owns Pixar now and so on, can do that, but only in very small video clips, right? So now it's become quite popular, actually, to have actors that have been dead for a while to resurface in some movies that were filmed just last year or last month, right? Like, what the hell? How could that happen? And yes, I mean, it can be done, but it's complicated. Now, machine learning in particular is introducing a set of tools right now that is allowing us to do this rendering very efficiently. And we can render human faces and their expressions in a detailed and unprecedented detail that is, I think, totally extraordinary. Okay. So it's happening, but not in image processing. It's happening in machine learning, right? And you might have heard a lot in the news about machine learning. And this is why, right? There's a lot of excitement because there are a lot of things that are happening that are actually making it really, really useful in many different industries. Okay, so this is what we need to solve, right? And I gave you a solution last time that maybe I can go back, see if I have it here, I guess. Right, so let me do this first. This is from last lecture, right? So we extended the rigid case, which was this one. This is the observation matrix as always. This is the rotation and translation. And this is the 3D shape, right? And want to recover the rotation translation of the camera and the 3D shape of the object. And in a structure non-rigid, you want to recover the shape of the object and the movement of the camera, but the shape of the object is different for every single image, which means that you need to represent the shape in a shape space given by the basis shapes, right? And then you have these coefficients of the basis shapes. And just because these coefficients, there are too many of them, you have to find a compact representation. And I showed you how to do it with the DCT basis, right? So that's a way to solve this problem. All right, another way, or a problem, let me start with the problem first. A problem with that method that we introduced last time is that you assume that these deformations of the object can be represented linearly. And by linear, I mean that you have a certain number of basis vectors, basis shapes in our case, right? And then how do we represent a shape in an image? My shape S is equal to the sum of my coefficients times each of the bases, right? So I'm going to have here S, my shape, equals to the sum over all bases, S sub I, right, times the coefficients, right? And if I have J here, Ij, right? So that's how it works. So let me call this maybe hat to make a distinction. So this is the 3D shape. These are the basis shapes, right? So this is, as you can see, a linear combination of the bases, right? So we are limited by this linear combination of bases. And the problem is that, remember, the number of coefficients I need to estimate could be very, very, very large. So one way to solve this is by representing in the DCT domain. The problem of representing this in the DCT domain is that you have to truncate the DCT basis. And if you do that, you either eliminate high frequencies, or you eliminate low frequencies, or mid frequencies, or the number of frequencies in between every two frequencies that you do add, right? You have to cut somewhere, because the more frequencies that you keep, the more parameters that you need to estimate. So something's got to give. So one solution that we derived early on, I'll show you this in a video. One solution we derived early on is to actually do this into portions of the object. So there are parts of the object, they're going to move in low frequencies, right? So for example, if you see someone walking, right? There are points like the center of mass right here that is moving like this, like a huge sinusoidal, right? Whereas there may be points on my foot that move very quickly, right? And so on. With the face, if I rotate the face versus the blinking, right? They're very different. So one way to address this is by separating these things. Actually, this is the wrong video. Separating this into different components. I don't see. Okay, hold on. Let me find. Oh, it is. Okay, good. All right, so I'll let the video describe the work, okay? I don't want to speak over the video, I guess. Can you hear?
Non-rigid structure for challenging problem in computer vision.
Can you hear?
Applications found in computer graphics,
Yeah, okay.
computer interaction, and biometrics. Given corresponding 2D points and multiple images of a non-rigid object, the goal is to recover the object's 3D shape and pose in each image. This is a very difficult problem with a large number of unknowns. To make this reconstruction task more tractable, recent research has attempted to define new constraints on the deformation of general 3D shapes. In this presentation, we first review the standard matrix factorization approach to non-rigid structure for motion. Then, to reduce the number of unknowns that need to be estimated, we introduce a compact model of shape deformation based on the discrete cosine transform. Finally, we propose a new factorization algorithm with complementary rank 3 spaces that defines new constraints on shape deformation. Here, we do not address the problem of tracking points over images. We assume that this task has been accomplished as a preliminary step. We assume that tracked points are given in the observation matrix W. Each pair of rows in W has the coordinates of all object points as seen in a single image. A column of W has the coordinates of a single object point as seen in all images. Here, the number of images is denoted by T and the number of object points by N. Let's review the standard matrix factorization approach. Remember, for each image, the goal is to recover the object's 3D shape and pose, is to explain the observations in W. The standard approach represents each 3D shape as a linear combination of a small number k of basis shapes. The basis shapes are the axes of a linear space where each object shape is represented as a point with coordinates given by the coefficient c. Using this representation, we obtain the standard factorization model. W is represented as a product of two matrix factors, M and S, with a low rank 3k, where k is the number of basis shapes. To derive a more compact model of shape deformation with fewer unknowns, we begin with the standard model and then we consider the common scenario where the 3D object deforms only gradually from one image to the next. Each object shape is still represented as a point in the linear shape space. As the object deforms, its point representation describes a smooth time trajectory in this space. The smooth shape trajectory is represented by the coefficients in matrix C. To define a more compact model with fewer unknowns, we represent matrix C in terms of the DCT basis vectors. With gradual shape deformation, a very small number of low-frequency DCT vectors is usually enough to model the smooth shape trajectory. As a result, the number of unknowns in our model is greatly reduced. To estimate the parameters in our model, we use the following matrix factorization method. First, we consider factor S as an implicit function of M and W. For example, the least squares estimate of S defined in terms of W and the pseudo-inverse of M. Therefore, the solution we seek is defined in terms of factor M alone. In the second step, we compute factor M as to minimize the reprojection error, as shown here.
This is important. So note that one way to improve the least squares, which I have mentioned before, but I want to reiterate because it's very important. One solution is to just give the least square solution, and that's given by the pseudo-inverse, right? We know that. But another way to improve over this result, remember, right, is by using the what's called reprojection error, right? So now that I have a solution for S, I can compute M times S here, right? Remember, W is equal to MS, so that should be equal to W. And now I can compare these two matrices. I compare them with the Frobenius norm. Remember the Frobenius norm, right? Because I'm just doing a one-to-one comparison. And that allows me to get even closer to the right solution, right? That tells me how well I do. That is the nonlinear least squares that we introduced early on in the course, if you remember, okay?
This is done using a Gauss-Newton optimization algorithm. Now let's consider two alternative ways of representing S as a function of M and W. The first method uses the least squares estimate of each column of S, which is defined in terms of the corresponding column of W in the pseudo-inverse of M. Because factor S represents the basis shapes, each column of S gives the deformation basis of a single object point. This deformation basis has 3k degrees of freedom, where k is the number of basis shapes. Therefore, all object points are modeled with the same number of degrees of freedom. A problem with this representation is that in practice, different parts of the object often present deformations of different complexities. This fact is illustrated in the following. The video on the left shows the motion capture data of a walking person. On the right, the image shows trajectories of points on the person's body. Note that
Okay, so these trajectories, what they are, take one of these points, and when this point moves in the image, right, it draws a trajectory. That's what you're seeing here.
body parts present complex deformations. Other parts present relatively simple deformations, and some parts remain nearly rigid. The conclusion is that with this representation of S, some points are modeled with too many degrees of freedom. They can introduce spurious deformations in the recovered shapes. For instance, when the extra degrees of freedom fit noise in W. To address this problem, we introduce a second representation of S, which we call complementary rank 3 spaces. First, we consider column triplets of M. Then, we can express W as the sum of products of a triplet and the corresponding basis shape. We can now define each basis shape as an implicit function of its corresponding column triplet and the residual component of W.
Okay, question, see if you're getting ready for the exam. Why did we select triplets for 3 columns at a time for MIs, these MI hats? Were they triplets? Because they span 3 space, right? Because the rank has to be 3, right? Right? Okay.
Modeled by the previous triplets. This representation can be shown to reduce the energy of each column of the basis shape as the index k increases. As in principal component analysis, the resulting basis shapes give a sequence of modes of deformation with decreasing energy, as illustrated by the image on the right.
If you don't know what PCA or principal components analysis is, it's just linear least squares by a different name, okay?
To evaluate our methods, we first use motion capture data and artificial 3D data sets. The original 3D shapes were projected to 2D to produce an observation matrix W. Then, a non-rigid structure for motion algorithm was applied, and the recovered 3D shapes were compared to the original shapes. The results of the two methods were compared to those of three state-of-the-art non-rigid structure for motion algorithms. Considering all 10 data sets used in the evaluation, the results of our two methods are in general better than those obtained with the other three algorithms. This video presents a visual comparison of the results provided by our two methods on a challenging walking person dataset. The reconstructed shapes are displayed in three orthogonal views and in overlay with the ground truth. The top row shows the results of our first method. The bottom row shows the results of our second method with complementary rank 3 spaces. Notice the better reconstruction of the motion of the legs without sacrificing accuracy and reconstructing the other body parts with relatively simple deformations. We now consider a face close-up video sequence of a sentence in American Sign Language. 75 facial points were manually marked over 114 images, but only one visible. Due to natural occlusion, 11.5% of the points are missing. The reconstructed 3D shapes are shown in 3 views. Finally, the recovered 3D shapes are shown in 2 views with the texture of a non-occluded frontal face.
All right.
Please refer to our website for more information.
So let me go back here. What was I? Here. So that's one way to solve this problem. Okay. There's another way to solve this problem, which is forget about the DCT basis. Now remember, this what I'm showing here are the same derivations that you just saw in this video, right? So this is the least square solution. Now, this solution that I have introduced here can also be written like this, right? This is the pseudo-inverse, just written in another way, okay? And if you substitute this into this equation, you get this equation right here, okay? You see that? I'm just substituting this term by this, right? And you get this huge term right here, right? Okay. Now, if you substitute this, then M transpose is given by, which is this term right here or this term right here, right? Same thing, is given by this, right? And this, remember, is the matrix of coefficients that we have. All right. This, it's a symmetric positive semi-definite matrix, and all symmetric positive semi-definite matrix define a metric in a Hilbert space defined by an inner product, okay? Now, this goes beyond your payday level, I guess I could say. But this is called a kernel mapping or the Graham matrix, okay? And all you need to know here is that that defines the metric of your space. Now, if you have what's called a linear kernel means that it maps x into x, so that when you compute the distance between 2 points, right, on a plane like this, you're using the Euclidean distance. If you substitute this kernel by a nonlinear function like, say, this one right here, okay, like an exponential function, now you're making this nonlinear, which means you are deforming the original space in some nonlinear way. So for example, 2 points that were very far apart, these 2 points here, by deforming the space itself may become really close to one another, right? So this deformation of the space is actually very useful to make this highly nonlinear functions in shape space that we were describing much more manageable, right? Ideally, potentially close to linear, if not linear, okay? And that allows then you to solve the problem with even the original rigid or close to the original rigid case by using a matrix of coefficients that is really tiny, right? You only need like a shape space of 2 or 3 dimensions to make to represent the small nonlinearities that you're given or that you're left with in this space. And this is what I was showing you at the end of last lecture for this phase example that I showed you. This is the space of coefficients that you need if you use a kernel, a correct kernel, to define the metric of your space, just 2 dimensions. That means that with just 2 coefficients, you can represent all the shape variations that the face can make. Extraordinary, isn't it? Now remember, you're representing, how many points was this? 70 something, I think? 70 something points, right? On the face, but 2 is sufficient in the coefficient matrix to represent, to define the position of these faces. And that is thanks to that changing metric in our Hilbert space, that deformation, okay? These are, by the way, called, if you're interested, don't write this down, reproducible kernel Hilbert spaces, okay? They're very famous. This would be the 2D dimensions, the 2D coefficients for Slinky. This is the deformation that Slinky makes. This is a shark. It's a synthetic image of a shark moving, and it's periodic, so there is a curve that comes back onto itself, right? And this is the walking sequence that you saw in the video. And this is, again, in the 2-dimensional space, the 2 coefficients that are required for this. This is a video of my former student dancing, some Brazilian dance, I don't know, which is very complicated. It has a lot of deformations, and still, you can see that the curves is more complicated, but you can still define it in this 2-dimensional space, which is, I think, totally extraordinary. Now, all this, as I said, all this is possible because of machine learning, okay? Only because of machine learning can we actually do these things. I mean, it's basically math, but, you know, math disguised for engineers. We call it either statistical pattern analysis or machine learning, just to make us feel a little better, I guess. So at the end of the day, you're just, as I said, deforming the space. But there's another way to deform the space, which is another technique. Don't write this down. Another technique that you would learn in machine learning or in computer vision if you take one of these courses, which is called regression. And what regression is that regression is very simple to understand. In general, if you have an image X, you apply a functional mapping F to get an output Y, okay? And this functional mapping from some space, so let me call, if I can find an eraser would be nice. Okay, somewhere behind. Okay, so F from some space F, say, to some space Q, okay? So it's a functional mapping. And what does this functional mapping do? This functional mapping represents here, what is shown here, this F is represented by this manifold, right? So consider this X and Y, or U and V, right? So these are image pixels, say, the U and V of 1 pixel, right? And then, for example, you have a 2-dimensional image like this, and you want to know for each pixel, for each U and V, which is the Z component, the depth component, right? That's what we're recovering in the structure from motion of the pixel that you're looking at. And there is a functional mapping that you know that's taken from this image plane to the three-dimensional reconstruction. That's what a structure from motion is giving you. But there is a way with what's called samples or data that you're giving into a machine learning system to find that manifold that maps directly from the image to 3D shape. Okay? And then you apply this function to this set of points, and you recover this three-dimensional shape. This is an example of a structure from motion algorithm working on a single image that can be used with kernels. And I thought, okay, I don't seem to have, see if I have it here. Okay, I don't have examples here, but but I can tell you that there are algorithms now. We have algorithms at this point that, given a single image of a face or any object that you want, just one image, one 2D image, you can reconstruct that object in 3 dimensions. And the reason we can do that is because that function f is actually modeling that mapping from 2D to 3D directly. So there are 2 ways to address this problem. One is the classical way, which we have covered here in this course. In image processing, computer vision, photogrammetry, you try to understand the equations of the physics of the world. You derive the equations of projective projection, right? You may simplify it as an affine projection, if you will. And then once you have these equations, you run it through the system. You have to end up with as many observations as unknowns that you have in your system of equations, or ideally even more equations than unknowns. So you can use least squares, right? And then you solve the system of equations, you find a solution. That's great. But another way to do that is to use machine learning. And that's a direction that people are moving toward these days. Okay? Don't get me wrong. All these techniques that we've defined here are extremely useful. People use them all the time. Right? They're very powerful. But in combination with these newer techniques, you can now do things that are unbelievable, I think. I mean, my guess is that in 5 to 10 years from now, you'll be able to generate video from text. Meaning I give you a text of what I want, right? So imagine an Adobe system on asteroids, right? So that instead of being able to edit the shadows or the illumination or change the expression of a face. Now, I'm going to say, I want that person. I may give you a picture of that person, right? Just one. I want that person to act that role and say these sentences in this specific set of emotions or emotional tones, and that other person to interact with that first person in such certain ways, and the system will just run through and will give you the video. We're close to that, within 10 years for sure. I think much earlier, but certainly within 10 years. So that's where things are going. And that is only possible because of a combination of tools that that I have introduced here in image processing, tools that I teach in computer vision, tools that you may learn in a computer graphics course, and tools that you will learn in machine learning, right? But if you know all these tools, then you will see how this is actually close to possible now. Which I have to say is super exciting to be working in this area right now. This is the time to be working in this area, but super scary as well. And we have to be cognizant of that. Because if I can do what I just said I could do, then if I could do it realistically, right, the video looks realistic enough, then you will no longer be able to believe anything else that you ever see again. And that's a scary thought. To me, that's a very scary thought. Now there are algorithms that people are developing to tell fake from real videos apart, and they work really well right now, but will we still be able to do that 10 years from now? I don't know. It's a scary future. So when I design these things, I always put a watermark in my videos that tells me this is a fake video. But is everyone going to put a watermark? Of course not. That's the problem. So you have to design algorithms to detect which things are real and which things are fake. And that's going to be a huge area of research in the years to come. So if you're looking for an interesting, exciting area, that's one of them. I'd highly recommend you look into this. We have to be very proactive on this because this is like doping. You know, dopers are always like 2 steps ahead of anti-doping technology. And by the time that you catch up to the dopers, they're already doing something else, right? And that's going to be the problem here unless we're very proactive, right? That we start working, and some people are, we start working now on how we're going to solve that problem before the technology can do it. And then the anti-doping is 2 steps ahead rather than detecting fake videos 2 steps ahead rather than the generating of the videos, right? But this is coming. This is going to have obviously huge influence in the movie industry, especially I'd say even for ads. You know, TV ads are very costly to produce, and internet ads, obviously. And you basically just run one ad over and over and over and over and over again, right? But wouldn't it be nice if the ad could be designed specifically for you, maybe even with your face or what have you, right? Or that the ad said specific things for you. Actually, Netflix got into big trouble for that recently because you know the little images that they show you for each of the movies or the shows that they have. There's a little image and the name of the show, right? That image you don't know, but it's designed specifically for you. Not everyone's is the same image. So there was this African American that was noticing that these movies that are basically only played by white actors were promoted with an image with a black actor. And it was like, how is that possible? And yeah, there is probably this one black actor that appears like 10 seconds in the movie. And that was the image that he was seeing. And it's like, am I the only person that this is happening to? So he started exploring, and he's not the only one, right? And then obviously, as you can imagine, it was like, what's going on? Because obviously you don't tell Netflix or anyone else what race or ethnicity you are. They just have to guess based on a lot of information that they receive from you, that you give them basically, knowingly or unknowingly, right? So this is going to happen with ads, and when this technology of creating videos becomes available, companies are going to use it. Obviously, it's going to be super powerful. It's going to be fantastic to be working in these areas. But as I said, at the same time, a little scary. So we'll see which one wins, if the scary or the excitement. But that's where we are at. Okay, I think I had maybe another video. This is a video of dense structure from motion from another group. I'm just gonna see if I can play it really quick here. So non-rigid structure from motion works also for images that are highly, or objects rather, that are highly deformable, like these things, right? So you could have a flag moving in the wind, or a piece of paper just folding like this, right? And structure from motion these days, it's powerful enough that it can still recover the 3D shape of a highly deformable objects. And I think it's actually extraordinary, the detail of reconstruction that you can get. So structure from motion is still a very active area right now, non-rigid that is, obviously. So there are a few problems that I have mentioned here that I go over in computer vision a bit more detail, which are projective projection. Everything that we've done here is fine, but obviously if you can use projective projection, all the better. I'm going to talk today a little about this, but I'm just going to give you some basic concepts to let you one more. This is like a hanger in a season-ending show, right? Or, when you're watching this series on TV, and the last episode of the season gives you hanging with something that's going to happen, and you don't know, and you have to wait like 3 or 4 or 5 months until the season starts over, the next season starts, and they do that because otherwise people wouldn't watch the next season. And then nothing happens, right? You watch the first show, is like, okay, that was it. But I'm going to leave you hopefully wanting to know more about the projective space, but that's a huge area that I do cover in some detail in computer vision. It's actually much simpler than it looks once you understand the projective space. But this, again, as I said, very interesting. So this one area in structure from motion. The other one is occlusions. What happens when you have occlusions? Another one is what happens when you have really long sequences, very, very, very long. That also creates another set of problems that need to be addressed. Noise, it's an issue, because as I said, we can use these machine learning algorithms to detect these fiducial points. But these fiducial points are never detected with extreme or with exact precision, right? And it's not that the machine learning algorithms are bad. The machine learning algorithms we have these days are actually almost comparable to humans. The problem is that it is impossible to determine where the fiducial point is. So take a face, for example, right? You can go home today, take a picture of your face, take a selfie with your phone, upload it into the computer, and then with an image software, zoom in into, say, the right corner of the right eye, right? And see if you can detect which is the pixel that defines, the exact pixel that defines the right corner of the right eye. And you'll see that's impossible, right? That doesn't exist. There's no such one pixel. So you're always going to be imprecise in one way or another, and you have to design algorithms that know that this is the reality of your world, that your world is digital, and that there is no way to define these things. So all these problems are very important and need to be addressed. All right, any questions before I move on? Or comments or things that you want to know? Now that you know all this material and you're going to do really well in the exam, and all these companies will want to hire you? Nothing? All right, okay. Let's see. This is just a deformation, detecting the deformation of this piece of paper, right? That's pretty cool. That's really cool. All right, so I'll stop that. And I'm going to talk about next, this is the last topic of this bigger topic that we've been covering on Hilbert spaces and Fourier and all that, which is the projective space. And as I said, I'm only going to give you a taste. I'm not going to cover this in detail, but I do want to give you some ideas that I think are very useful to know, because I know many of you are just doing, some of you are undergrads, right? And some of you are master students are not going to continue on a PhD. So I think that you need to know these things if you want to put that in your CV and apply for some job out there, because they are going to ask these things, and you should know what these things are, right, and what they represent. Otherwise, yeah, you're not going to get that higher that you want. Okay, so to understand the projective space, let's go back to the parameterization of lines, planes, and especially the circle. Let's work with the circle, or the sphere in general, okay? SP minus 1. So if in p dimensions, in the space of p dimensions, Rp, I have my hypersphere, which is SP minus 1, right? So first, let's remember what we introduced in these last lectures. We have the line, right? The line is a line that goes to infinity and negative infinity in each direction, right? So it goes to infinity here, or plus infinity, and negative infinity on the other side, right? And this is just R, right? The real domain. Or R1, if you will. And then the plane is nothing else than these two lines, right, that define 2D space. And this is R2. And these two lines are orthogonal to one another. And then in R2, I can define the circle, which is S1, right? Now, if I want to define the circle, I can just place it here in this representation of the plane, where I have these two axes, say the x-axis and the y-axis, right? Okay. And what we did early on, remember, that was like, my goodness, I forget, was that like the second lecture of the course, that we provided the parameterization for, well, actually two parameterizations, right? One in non-homogeneous coordinates and one in homogeneous coordinates for the circle. Remember that? And when we were doing that, what parameterization did we use for the circle? We used the classical parameterization that we most typically use, right? Which is, anyone can remember what it was? Classical one. X square y square equals r square. Very good, right? That's classical parameterization, right, of the circle. But this is not the unique parameterization of a circle, right? I can define the circle in multiple different ways. We just did this in our last lecture, didn't we? Where we defined the circle using the cosine and the sine, didn't we? We said if every point on my circle, right, is defined here by, if this is the angle, right, by this value, which can be given by the sine of the angle, and this value that can be given by the cosine of the angle, right? So this will give me this y coordinate here. This will give me, the cosine will give me the x, and this the y. So I could define this as a function of the angle, which is the cosine, right? This value right here in the x-axis, and the sine. And there you go. That's another parameterization of the circle, right? There's nothing intrinsically wrong with it. There's nothing intrinsically better with it. It's just a different parameterization. Here, obviously, the angle goes from 0 to 2 pi, right? And that covers the whole circle. And we use this parameterization also when we talk about solid angles, right? We use that all the time. Very useful. All right, I want to talk today about yet another parameterization of the circle and the sphere, and a moduli space parameterization in particular. Of the circle by a moduli space, I mean a space of possibilities, okay? That just means the space of possibilities that I have. And the way I'm going to do that in 2D space, obviously, because it's a circle, right? So this is R2. This right here, as always, it's my origin, O, right? And now what I'm going to draw, I'm going to take all the lines that go through the origin, okay? So if I take this origin, and now I draw all the lines. Here's one, right? Now this line, what this line really defines, it's a subspace of the original space. This original space is of 2 dimensions. This line defines a 1-dimensional subspace, okay? So this is subspace. And you could say this is a 1D subspace of the real domain of 2 dimensions. Now, by definition, a subspace is in 2D a line that goes through the origin. Now, all the lines that go through the origin are a subspace of R2. In more dimensions, if I'm in RP, then a subspace of Q dimensions, Q is strictly smaller than P, is a hyperplane of Q dimensions that also crosses the origin. Okay? And a subspace always divides the original space into 2 halves, 2 half spaces. Okay? And 2 half spaces are affine subsets. Okay, or affine spaces. So, okay, here's one subspace, here's another, right? That's another possible subspace. Here's another. Let's see, here's yet another. Here's another one, right? Here's another one. And so on, right? You can have this one here. All these subspaces, right, go through the origin, and they are 1-dimensional subspaces of R2, all of them. Okay, so here's what I'm going to do now. I'm going to take advantage of this set, okay? This set of subspaces, or 1D subspaces. And what I'm going to do, here's my 2D space. I'm going to take a circle, S1, but this time I'm going to put it over here. Okay? Such that this, say, this would be the south pole, can you see that, of the circle, okay? Touches the origin, okay? It's tangential to the origin. Now look at this. This is really cool. And this is super cool. Every time I do this, I love it. So you have all these subspaces, right? So let's redraw them here. This is one subspace. This is another subspace. This is here another subspace. This is another one. This is another one. And so on, right? Okay, so far so good? Okay, each of these subspaces, all these subspaces, crosses this circle S1 at 2 points. One is at the origin, and the other one is defined at this intersection here. Right? Okay, everyone in the back? Yeah? Now there is an exception to what I just said. So all these one-dimensional subspaces crosses the circle at 2 points, the origin and one of these other points, except for one subspace. Which one? The x-axis. Very good. Which we'll say also does, but at infinity, right? But minor detail. But the x-axis only crosses it at, obviously, the origin. So what I'm going to do, I'm going to parameterize the circle now. Using these lines, these subspaces, or I should say 1D subspaces. And I'm going to do that next for the sphere. Actually, I'm going to do the derivations for the sphere because I want to do the ones for the circle and then the ones for the sphere because they're one and the same. But you will see, bear with me, that we're going to end up with this notation, 1 minus x squared, 1 plus x squared for this first coordinate, and 2x 1 plus x squared. That's a parameterization that we're going to come up with for the 1D. And what does this represent? This first component corresponds to, right, this position, and this other component corresponds to this position, right? That's what we're interested in. That's just a different parameterization. Okay. Okay. So let's see how we can do, before I say that. Now, the important thing about this, the reason I'm talking about this is because the space of all one-dimensional subspaces, so the space of all one-dimensional subspaces, as we have defined them here, is called, anyone wants to guess? It's called the projective line, or I'll call it P1. Okay. And what does this mean? This means that I can represent all of these 2D space just using one dimension. That's what it really means. In the same way, I can represent 3D space into 2 dimensions. Let's see that. So now let's imagine that I have a S2. So that would be the sphere here looks maybe something like this, S2. And I'm going to have to draw now my 3 axes. So if this is the origin, this is going to be one of them. This is going to be another one of them, right? And there's a third one that goes in this direction. Yep. Okay. Let me take that plane. So if this is, I don't know, x, y, and z, or whatever you want to call it, then let's take the xy plane, okay, or ij plane, if you prefer. So this ij plane, it's a 2-dimensional plane here, which can be parallel to it, but I'm just drawing that actual plane that goes through the origin here, right? Now remember that I have that point down here. That's the same point I was using here, right? Call it S. That's at the very bottom of the sphere, right? At the very, very, very bottom of the sphere. That point S. And now I can draw a line, one of these one-dimensional lines I was drawing here, right? One of the infinite possible lines. I can draw a line, and it will cross the sphere, right? In the same way that here I cross the circle. Now here it goes through the sphere at some point, I don't know, let's call it Q, right? But it also goes through that plane, right? The plane that I have here at, say, point P. So that point P has coordinates x, y, and 0, because z, that direction, is 0 for all the points P. S, what are the coordinates of S? Anyone? Zero. Very good. 0, 0, negative r, right? Where r is a radius. And now what do I want? I want to define my vector from S to Q. Now, to define that vector from S to Q, I can take this here. I can take first the coordinates of S. So this is 0, 0, negative r, right? And now I can take, I'm going to take this vector right here. See this vector right here? This is a vector PQ, right? Or actually, no, I'm not going to take this one. I'm going to take this other one, SP, this vector here. SP vector, right? That goes from S to P. So I'm going to write S to P. And what do I know about SQ? SQ is SP multiplied by some scalar, right? Let's call it T. Here's T. Yeah. Okay, so SP, so this is 0, 0, negative r. T, SP, it's going to be x, y, r. And, right, r, because that's the distance. And now this is equal to, let's see, 0 plus tx. So I have tx. 0 plus ty. Ty, and negative tr squared. No, I did something wrong. What is it? Tr, I'm doing something wrong, and I don't know what I'm doing wrong. negative r plus tr, right? Yes? Okay, now we also know that Q is on S2, right? Q is actually on the surface of my hypersphere, meaning that this point here, Tx, Ty, negative r plus Tr, this, oops, actually, let me do it this way. The first one, Tx squared plus Ty squared plus negative r plus Tr square, that has to be equal to r square, right? Because this is the equation of the sphere, right? And now let's take r equal to 1 to compute this. And if you compute this with r equal to 1, you're going to get to the result that t is equal to 2 over x squared plus y squared plus 1. Which means, if we come back here, that Q is going to be equal to 2x 1 plus x squared plus y squared 2y over 1 plus x squared plus y squared, and 1 minus x squared minus y squared over 1 plus x squared y squared. And those are the coordinates of Q. And if you reduce this to just 1, you get this equation, right? Right here. This right here is called the stereographic projection. And there are two super cool things about this. First, have you ever by any chance seen a map of the world? Right? You might have even had one on your wall at home in your bedroom, or definitely at the school somewhere. There was a map, right, on the wall, a flat map on the wall of the school with a map of the world. Wait, wasn't the world a sphere? How do you map from a sphere to a 2D plane? Stereographic projection? That's how. It gives you a unique 2D coordinate for each point on the sphere. This is super useful in a variety of things. So let's get back here. For every point Q, I'm going to have a unique P, right? So if I now drew, say, another point here, right? I drew another line, and this goes through here, and P is here now, right? And it gives me a unique one. And if I go, say, in this direction, right, I'll cross here, and maybe here, and so on. You see how this works, right? For every one, you're going to get one. Now, of course, the closer you get to the tangent of S, right, the farther away you need to go in that plane. And there are different types of mappings that allow you to shrink this, right? And the more you shrink it, the more deformed the world looks. So when you look at the map of the world on a wall, it's shrinked so much at the poles, because obviously know that if I want to visualize the poles, I have to go to basically at that point, which is tangent, I have to go to infinity, right? It's impossible for me to visualize this on a wall, on a finite wall like this one. So I shrink it, and then I get really weird scales, right? So in the map, you look at Australia, like, oh, this is a small country. Yeah, it's only the second largest country on Earth by size, right? But it looks tiny in the map because of this fact, right? And so on and so forth. Obviously, there are many things or many implications when you use this. As I said, one of these implications is that this point is projected to infinity. So that point S, when I project, is going to be infinite, infinite, and 0. Now, this is weird, but we have a way to represent this. You know, a way to represent this in homogeneous coordinates, right? And you can represent points at infinity. So it's very powerful when you start combining these ideas with homogeneous coordinates, which I will not do here. All right, so these techniques allow me to represent the hypersphere into a hyperplane. Okay? And that's going to be the projective plane instead of the projective line now, the projective plane P of P dimensions. Okay? And that's what I'm talking about. This is a really powerful tool that you can use. It's interesting to note a couple of extra things I could probably talk about if I have time. It's interesting to note that, let me see if I can draw this. This is easier said than done. Okay, so here's my sphere. Okay, and now let's see if I can draw this plane. This is my origin. This is the plane that cuts through the origin. Okay. Now, let's say that, so this is my point at the very bottom of this sphere. This is S2. Now, let's say that I have 2 points, P1 and P2, on that two-dimensional plane. Okay? So far, so good. And now I have this line, right, that defines P, and this other one that defines P2, right? Yes? So far, so good. And what do 2 points define in a plane? They define a line, right? These 2 points define a line, a unique line. Right? These 2 points define a line. Any 2 points in 2D space define a line, right? Or any dimensionality. Now, how do I represent this line on the sphere? Any guesses? What does a line map to on this sphere? A circle. Very good. Why? Very good. Because, look at this. Now, if I take this point, right, and that point, I can draw a circle that has to go through this, and this, and this, right, like this. Now, this circle is not on the surface of S2, cuts inside S2, right, or I can carve it on S2, like a curve, if I want to, right? But this circle is the one that connects all the points that define all the lines, right, that go through this. You see that? So lines on that plane correspond to circles on the sphere. And circles on the plane also correspond to circles on the sphere. Oh, I can, yeah, let me do this. It's a good idea. I have this in my notes. You can do this in a cross-section if you prefer, maybe clear. So if this is the circle, but this is not S1, this is a cross-section of S2, right? And here you have a line segment that you want to represent in that cross-section, right? You're going to end up with this curve, right? And if you have a plane and a sphere, let me draw maybe the sphere now underneath, because you can put the sphere where you want, really, right? So if I have my sphere here, and now it's tangent to that plane, and I have now a circle here on that plane. Now this also corresponds to a circle here, right, that is projected, a circle, onto that sphere. And that we used that idea when we defined solid angles, remember? And we approximated this by making this a differential. We approximated it with a plane, right? So this allows us to work out the equations of projective projection that are so useful and desirable for image processing and computer vision. So that's one thing that can be done with this. Another thing that this is useful for is to define quaternions. I see people taking pictures. I have good drawings in the slides. This is really bad. I do what I can, but I'm not a computer. But the slides that you have on Canvas have these exact same things, but well drawn. And I'm sure that if you Google it, you can just find it. It's not that complicated. This is famous. I'm not describing here a secret, right? These are famous results. Oh yeah, so I was going to say, I don't know if I should cover this because the time is tight if we want to cover this. Maybe I can give some ideas. But another application of all this is quaternions. And quaternions are very useful to define 3D rotations, okay? And the thing is that quaternions are defined in 4D space, right? So complex numbers, but in 4D space. And very useful for generating or for interpreting images. And they're also very useful in computer graphics, because computer graphics at the end of the day is nothing else than the inverse of everything that we've done here, right? So here we go from the image to the model, and computer graphics goes from the model to the image. So they're one and the same. So these things that you have learned here are both very applicable to computer vision and image processing, but as well in computer graphics. All right, I'll see if I have time to maybe sketch a few ideas of quaternions in our next lecture. If I see that we're running out of time, I do want to move on to our last topic of the course, which is color vision, okay, and color perception, which I think is very important. It's very important that we understand first what color is, what color perception is, and that we can define the models that we're going to use to represent color in images. All right, I'll see you next week.